I'm John McClune from the Technical Communication and Strategy Group, and one of the fun things that I get to do for the company is write for the company blog. So in my talk, I'm going to share some of the code that I've done, some of the fun that I had writing it, and where some of the ideas come from. So it's billed as a hands-on, so I've provided a download link here for the code if you want to play along as I go through stuff. Although unfortunately I just discovered as I uploaded it that it's about 40 megabytes, so it might take a minute on our network to get down. So let's give everyone a second just to write that code down if anyone's planning to. I'll show it again at the end. So we figured that by the time everyone's got some lunch inside them, they'll be a bit too sleepy for the kind of hardcore intellectual stuff that a lot of the talks are. So this is meant to be a bit of a light break. Those who know me outside the company mostly know me because of stuff I write for the Wolfram Blog, since most of what I do for the company is fairly anonymous. And so we thought it'd be fun just to talk about some of the things that have come out of stuff I've done for the Wolfram Blog. So a few things just as a background to put it in context. The blog, of course, is a marketing outlet for the company to show people, showcase the product and tell people what the company's up to. But unlike a lot of the marketing we do, it's completely undirected. So in 2006, when it started, I got an email from Stephen Wolfram saying, "We're starting a blog, could you write something for it?" That was the direction I had. So I wrote some fairly bland piece about what I'd just been doing that week with Mathematica and sent it off, and that was, I think, the second item on the blog, but it wasn't really very interesting. And it wasn't until a week or so later that Stephen sent me a one-liner piece of code that said, "Hey, maybe this would be good for a blog item." And I looked at it and I thought, you know, that's kind of rubbish. I can't make that interesting. And I got playing, and I realized that I found my way of doing the blog, which is just to have fun with Mathematica and then write up the fun that I have and share it afterwards. So I have no great agenda myself with the blog. What I do is just play with Mathematica and see what comes out. And so the result of that is that for a bit of self-promotion, I have half of the top 20 viewed blog items on the Wolfram Blog, and including the top blog item that we've had ever so far, and I will reveal what that is at the end. So that'll reason to stick around to the end of the talk. So I thought I'd run through a few bits of fun code that I did by answering the real question here, is what do I find fun, and so what do I end up writing about? So the first thing I find fun usually, and Mathematica is great for this, is having no idea where you're going and just wandering around. And so the idea that got me onto this track was when Stephen sent me this one-liner here, which was to look through the color data for names of colors, and then look through the descriptions of flags of countries and find intersections between those words and add them up. I thought, that's not how I would have done it, and I've got to keep Stephen happy, so I thought I've got to do something with this. So my thinking was that you can't use words, you've got to use numbers, and so I figured what we should actually do is look at the images and do some real analysis on them. And so I wrote this quick function here that takes the image data for the flags from the database, throws out the alpha channel, because that was getting in the way, and then looks for a tally of all the colors in there with some difference measure to when colors are too similar, because I didn't want hundreds of different colors with one pixel each. And so you end up with the ability to pull out the dominant colors and their frequency. These days, of course, it'll be easier with the dominant colors function in Mathematica, but it didn't exist then. And what I realized, of course, is once you start answering questions, you start asking new ones. So I said, okay, well, so what happens if we add it up over the whole world? And so this is adding the different colors that are available across all of the world's flags. And I thought that's not really very fair, because Tuvalu's got about 200 people living there, and China's got 1.4 billion. So maybe I should add it up weighted by the population of the world. And then I started thinking, well, what's the average color of a flag? And started plotting that across the world. And thinking, is there some social trend here? So I started thinking, well, what if we do a smoothed moving average by borders and figure this out? And I thought, these all seem really different to their neighbors. So I had a hypothesis that maybe, because flags were about having something to wave in battle, and you're normally fighting your neighbor, that maybe the colors of your neighbor's flags are disproportionately different to yours. And so I wrote some code to test that hypothesis, and it turns out not to be true. You're actually more likely to have similar colors to your neighbor than opposite. But once I'd done this, this was my thing set, that this is how I go about the Wolfram Blog items. And I think much of the popularity comes from the fact that I'm doing real technical stuff in the blog, but I'm not too smart. So my stuff's fairly accessible. There's some very clever things in the blog that sometimes are hard to read, and some fairly bland things that have no technical content, and I sit right in the middle. So the next thing I find fun is turning a chore into fun. I have to learn Mathematica a lot. Every year or so, I've got 1,000 new functions I have to learn, and some of them I don't even have the educational background. And so I've always got this challenge of, great, we've got image processing. I don't know any image processing. How do I learn it? So what I usually try and do is think of something that I can explore in order to learn the new functionality. So this is something I did when we first shipped image processing. I looked for something to process, and I was tidying up after the kids and found this music box. Oh, no, I don't want actual size. Probably somewhere in between. And I thought, well, what if we were in real archaeological situation? It'd be all rusted up, and I wouldn't be able to turn the handle. Can we tell what the tune is? Seems like a good image processing thing. We just have to identify the blobs. And so I learned about things like slicing images to take parts, and then you have to start thinking about how do we get rid of the noise? Well, I could try blurring, but in fact, there's a curvature here that is kind of weird. So I wanted to try and I found that edge detecting in one direction only seemed to work. So I had a blur to get rid of the details, edge detect only horizontally, sorry, only vertically, in order to start picking out the blobs. And then I figured, well, we need to do something to thin those down. So I turned it into black and white and shrunk the blobs a bit. And now we've actually getting the blobs out. I had to write a function at this point to, if you look at the original blog, we didn't have component measures in those days, so I had to write something to try and measure where the center of each blob was, but that's fairly easy to pull out. And then we've got the actual data. So here's a musical score from that, and revealing my, I didn't plug into the microphone, so you probably won't hear this, converting that into sound notes. You can just about make out it's happy birthday to you. And this took a bit of tuning. I am not musical, so I was trying to adjust, well, what is this function here to turn the vertical heights into sound notes? And I tried to persuade one of our musicians in the company to help me, but she wouldn't touch the code. And this sort of hits on another thing I love doing in Mathematica, is trying to mix different things in Mathematica, because I'm always preaching about how it's an integrated system, and I kind of find it cool that I can go from a picture to data to sounds all in one system. So here's another one that I did as still learning image processing. I started trying to figure out how do we do things like content detection. And so the idea was that with this, let's see if I can get my webcam to talk to me. Here it comes, it's waking up now. So the idea was that I would take a couple of images, and this one's got a 2-second pause on it so I can step out of the way. And then we could detect if something has appeared in the scene by looking at the difference between them. So the obvious thing was to subtract them. You ended up with quite a lot of noise, so I did a bit of blur on both again to try and get rid of it, get rid of the noise. So I've blurred each image and then just done image difference. And you see now this wood texture here has gone completely black because it was the same between one scene and the next. And so now it's a case of putting a threshold on that, and we can pick out the thing that's new in the scene. Where my jacket's a bit dark, it seems to have blended into the background, but it's not done too bad a job. And then I wanted to try and clean up the edges of this and fill in some of the gaps, because I don't want to see kind of holes for the eyes. And so closing is something that shrinks the holes in an image. So all these small black areas have closed up. And then it's simply a case of packaging all of that into a function that says, can we just find the scene changes? These are all the steps in one. And the highlight was to take the image and find the edge of that to put onto the frame, and then wrap it up into a function that measures where enough image content has changed. Now, as I said, I like to mix different bits of Mathematica. So in the actual original blog item, I went a bit further, and I added code to run a regular script every 30 seconds for changes, and then email me with the differences. And of course, like I said, I like to have fun, so despite the embarrassment of it, here's me dressing up as a burglar and stealing something from my office for the amusement factor in the original blog. And another one from this sort of stream of trying to learn things was when we added graph theory. And again, I don't know much about graph theory, so I thought I should try and figure out something that had a graph to it, and then do some exploration on it. And so I had this a pair of blogs about word ladders and edit distances that wants to find, and this, I better get this running because it takes a few seconds. So while I'm explaining the code, I will get the graph being built for the 5 case. So let's walk through the code here. What I had was to take the word data, so all of the words in the English language, I'm going to find ones that are of the length n, because word ladders, the idea of a word ladder is to get from one word to another, changing one letter at a time, but you have to always have a legal English word in between. So you can't just change a random letter and make a meaningless word. It always has to be a real in-between word. And so since the version I was looking at doesn't allow for adding and deleting letters, I grouped them into a class with one length. And then the graph is simply a case of making a graph out of all the cases where the edit distance from one word to the next is of length 1. So if they're one edit apart, then there's a connection between the words. If they're not one edit apart, there isn't a connection. And you do that across all permutations of the words, and you end up with this graph. So this is the graph of edit distance words of 5 letters. So these words here are only connected to each other. There's no way to get from that word to that word by a word ladder. And likewise, all of these are isolated, and ones that don't connect to anything don't show at all in this graph. But it is possible to get all the way from whatever this word is to this word, going through legal words along the way. And the next rest of the graph was then to try and figure out what's the longest minimal route across there to make a puzzle. Unfortunately, one of the few things that is imposed on me by the blog is I have to keep the things clean and politically correct. And unfortunately, one of the words that comes out if you run the code on its own turns out to be slightly obscene. So I had to delete that out of the database before I started. It was just my luck that when it came up with the best solution, it runs through a rude word on the way. So this is what drives a lot of what I do, is just trying to figure out how mathematical works and always trying to be motivated by something fun along the way. So another thing I find fun, which I don't know if it ought to be fun, is reinventing the wheel. I was never a very good student, and I hate reading academic papers in great detail. So when I look at something that I want to solve, I have a tendency to never read the documentation and never read how it should be done, but just try and figure it out for myself. It seems more fun that way, even though it probably takes me longer. So these are a couple of ones where that was the philosophy I followed. There was a news item in the US about some Russian, I think they were Russian spies that got deported from America after their computer broke down, and they took it in for repairs, and it turned out the repairman was an FBI agent who was looking at the steganography they'd been using. I thought, steganography, I can do something on that. I don't know how, but I'll figure it out. Something to do with least significant bits. I'll figure out the rest along the way. So this is the way the code rolls out, is you can take an image, and I convert it into bytes. Pretty straightforward. So I always like to throw in personal stuff as well. This is my chicken, Matilda. And the idea is then you and away the last bit. So for each color channel, there's going to be 8 bits of information, but you can't actually tell the difference. If I do this for the whole thing, it still looks pretty much like the original image. So if you compare the source image to the output image, to the human eye, they look identical. And even if I do the difference between them, unless you've got a really good monitor, there's nothing to be seen there. So it seems like they're the same image. But in fact, if I turn up the contrast on that, then you'll find that there's all kinds of information in there that I've swept aside. So that's the real difference between the two, is that tiny bit of gray at the bottom. And that's the place where you carry your hidden message if you're going to do spy stuff. So it turns out after that, because Mathematica serializes things so easily, that embedding things in that secret message is fairly easy. This is slightly different than the original code, where I start off by taking whatever our message is, serializing it into an ASCII string, turning that into a bunch of numbers, turning that into binary numbers, flattening the list so it's just a stream of bits, and that gives me my secret message. Our carrier message is what we had before, just drop out the bottom bit. And then all I have to do is distribute those bits over the message. So 1 bit goes, well, 3 bits, in fact, go into each pixel. 1 in the red channel, 1 in the green, 1 in the blue. And that's what the rest of the function does, is it, trying to find the bit here where it does it. I can't even follow my own code now. So partitioning it into 3s, and I have to add it somewhere to add in the secret message onto the carrier message. And I also insert a little first 60 bits I use to tell it how long the message is, so that I'm not having to put in a whole bunch of padding. And the extractors does the opposite way around. You rip out the bottom bit and turn it into a string. So this is the effect. You have a picture, you insert your secret message, if I copy that picture and put it into the deconstruct, then out it pops again. And you can hide all kinds of stuff in there. And by the beauty of compression, I can put a whole JPEG image in the JPEG image that's larger than the original image, as long as I send the compressed message. But it turns out, because Mathematica's symbolic stuff works really nicely, you can send anything that Mathematica has in this. So I could send, for example, some interface and embed that in the image. And now if I decode that one, then we get out an interface. So this sort of automatic serialization just means that once you've got this steganography tool, you can hide anything you want in it, which is kind of cool. So I'm probably on the CIA watch list now after that. So another one on this was rock, paper, scissors. I was thinking about doing this for our computer-based math statistics course. And there's a lot of code here, which I'm going to skip through because it's mostly user interface. So all of that top part is user interface, and the actual logical code here is at the bottom. But the idea is that it's the classic game of rock, paper, scissors, and I can put in my guesses on the left and it guesses on the right. My daughter got me onto this because she showed me a solution to this that cheated. It waited till you chose and then just did the next one round. And I thought, no, we can do better than that. We can do something that actually uses some maths. And I'd read about this theory that we could analyze the past history for lack of randomness. Because, of course, if I play this completely randomly, I shouldn't be beatable in the long run. But humans are not very good at being random. So here's the logic that the actual bit behind it that I had worked on. So here's the structure of the history, that 1 is rock, 2 is papers, 3 is scissors. And the first is my move, and the second value is what the computer did. And this is the stream of history, and we accumulate this as we go along. So the idea is I've got to seek through that. For the current situation we're on, when has that happened before? Well, 1, 2 happened here and was followed by 1, 1. And so if I do that, it'll seek back and find the next move that happened after that. And this is a parameter of how far back it looks. So if I change this to a 2, it'll look for when this sequence occurred, which will not have been any time in this short sequence of data. So it doesn't find anything. And I realized that there's not much data at the beginning, so I made it slightly more complicated by deciding, well, we could look at the whole history, or just your history, or just my history, and see which one is the biggest influence. In the end, the all history is all that matters if you've got enough data, because it all comes out. So having sorted through the history, then you can use that to make a prediction. Well, then I got stuck, because I had competing predictions. That what happens if we look at a history of 1, and it says it's going to be rock next. But if we look at a history of 2, it says it's going to be paper next. And I thought there's got to be some way of weighting them. Do I weight them by which is the longest history, or which has occurred most times? And I was stuck, and I put it away and forgot about it for about 3 or 4 months, until I was writing computer-based math stuff, and we were trying to explain hypothesis tests to the students. And I suddenly thought, hypothesis tests will solve this. And so I dug it out and said, in the end, the way to resolve the conflicting recommendations is to find out which one is statistically most significant if compared to randomness. So it might be most significant because it's really biased, or it might be only slightly biased, but we've got a huge amount of data that really justifies that, and we don't care. So all I have to do is take some sequence of past values and compare to what would be a random player, and get a p-value out that says, okay, this would be very unlikely to have happened by pure chance. So there's some bias, like this person really likes scissors. And if I put in a bit more variety into this, you'll see the p-value becomes much bigger. So in the end, all I had to do was go through all the predictions, give them all the p-value, and just pick the one with the smallest p-value. Now, I don't know if it seems like abuse of p-values, but it actually seems to work, that when I play at least, up to about 50 games, it doesn't do very well, but after about 50, it starts to creep gradually ahead, and it can be quite fun trying to outthink the computer by setting up patterns and then deliberately switching. So there's probably still some improvements that can be made. So another thing which I've already mentioned that I find fun is mixing different kinds of maths. And I sometimes try and go out of the way and sit there and think, how could I mix graphs and images? Or how could I mix other bizarre areas? And so partly affects the way I try and solve things, but also sometimes I just go out and outwardly try and seek some cool way of mixing them together. So this is one that I quite like, that I read XKCD. It's a nerdy comic strip that's written by, I think, an MIT guy called Randall Munroe. Quite funny, starting to run out of ideas a bit now, but I've tended to follow it. And I came across this cartoon he did, which was a self-description cartoon. So it's got various charts that are a reference to the charts themselves. So the total amount of black in this as a pie chart is this. And the amount of black in each of the 3 panels are these 3 columns. And then this is a plot of where the black is in the image. So I thought that's kind of cool. I love recursive things. And so I thought, I wonder if we can automate this. So most of the work is in recreating the charts. So I'll just skip through all of that. There's a function that creates each of the panels according to the data you need to pass in, and a function that puts all 3 together. And then I had a quick function here that that rasterizes the image into black and white, and then counts the number of pixels, because we need that as a fraction. So for example, this string has a black fraction of 13%, whereas if I do something like an X, that has a black fraction of 25%. Now, the idea that I realized was something I'd loved when I did numerical analysis, because as a schoolboy, of course, I've did what every schoolboy does when they get a scientific calculator and don't know what the functions are. You press them over and over again and see what happens. And so unwittingly, I learned the numerical analysis way of solving cos x equals x. If you keep applying cos to it over and over again, then eventually it converges, just like it does if you sit there tapping the cos key on a calculator. And I realized that this is the same problem. Instead, what I'm trying to solve is the problem for the cartoon image is equal to the black analysis of the cartoon image. I'm trying to solve that equation. And that struck me as a really cool idea, that we got an equation involving cartoons rather than x. So I'm going to do exactly the same thing with this calculation, which is that I start with an empty grid, and I generate, here we go. I generate the grid based on emptiness. So here it is. There's no white in an empty grid, so the pie chart's all white. There's no white anywhere, so the bar chart is empty, and there's no white anywhere, so the plot's empty. But now I can call the same function on this and analyze this image. And so the black fraction is calculated and thrown back into the image. And now on the next iteration, you find the one we were just looking at had 9% black. Sorry, 97% white, 3% black. And that most of that black was on the right-hand side of the image. And so now it's just a case of reaching a fixed point in that, and in practice it converges after about 10 iterations. So you run this, calling that function on the output over and over again about 10 times, and you end up with a solution that comes fairly close to Randall's.
Did you make fixed point work?
Fixed point did not work, actually. The reason is that the anti-aliasing causes little jittering pixels, and there's only 1 pixel changing perhaps between one image and the next, but as far as fixed point's concerned, it still hasn't converged and it goes around again. So I would have to have done some same test that gives some tolerance, and by that point I thought I'll just do nest, and there we go. Obviously, not everything is amenable to this because you've got a convergence criteria, and while they taught me how to tell whether things like cos converge, I couldn't apply that maths to cartoons, so I just played around with things that converged and things that didn't. If you do this in CMY color, it converges. If you do it in RGB color, it just goes divergent and gives you rubbish. But it was kind of cool, and Randall Munroe wrote to me a little bit later to explain that he'd done it by hand with Photoshop and the image measuring tool and redrawn the cartoon by hand over and over again to achieve the aim. Oops. My favorite design failure that I reported yet again in slideshow mode. If you close the whole group, it disappears. Okay, so another one which was sort of mixing things was this one which I did. Another thing I like is winning. I'm a bit competitive, and so I did this blog that did a quick sort of attempt to solve a maze that's just around the corner from our office by picking out the white, by binarizing the image, deleting any small blobs, thinning it down to lines, and pruning all the dead ends. And I got this sort of semi-solution, but it doesn't deal with loops. And I published a blog on that, and I felt a bit guilty because I kind of stole the idea from Roger Gomanson, and all I did was apply it to a real-world problem. And then Danny Lichtblau, who does a lot of our calculus work, who's much, much smarter than I, did a response. He wrote to me and he said, well, you could have done it this way. I said, write it up. And so he wrote it up, and it looked a lot better than mine. So I thought, I'm going to have another go at this. I'll go back and see if I can improve it. And that's when I hit on, well, the idea you could mix graphs, because this is looking a bit like a graph. So my better solution started the same way as before. I crop it so that, really just so that I've got a start and end, because otherwise the solution to this maze is don't go in the maze, just take a shortcut to the end and leave. So that was just a practical thing to make a clear start and end. And then I take from that, I find the position of all the white pixels. So I'm trying to find anything that is white in the data of this. So I get a list of all of the coordinates of the paths. This is just a search for the coordinates of those 2 pixels at the beginning and end. And then a slightly complicated function that says, can we find the neighbors for a particular point? So it's the 8 pixels that surround the point that we're looking at. And then I can make a graph now that I've got that function. I simply go through all of the points, all of their neighbors, and if the neighbor is white, we've got a graph connection. And so there's the node for the start, and we can generate now that across all of the pixels. So that takes a few seconds to run through. And you end up with sort of the London Underground map of this maze. This is sort of topological version, but the coordinates have been thrown out. They're just hidden in the name of the vertices. We're only looking at their relationship now. So now I can apply graph theory functions, and graph theory has find shortest path. So that's easy. I'm done straight away. And now I just have to convert that back by finding all of the things on the path and generating an array out of those using their names, and we've got our solution. And we can overlay it on top, and there's our answer. It's actually not quite correct. In the original blog, I have to do a little correction here because this is actually a bridge. And so this involves climbing the bridge and abseiling off this bridge. So in fact, you go under and round and back under, which the only way you could do that is with manual intervention by clipping out the pixels that join these 2 paths together. So another thing that I find fun is extremes. So we had the word ladder one earlier, and what often comes out with these things is I think, well, what's the most or the least? Or what if I apply the function to itself and make it compete with itself? So the longest word ladder came out of that if I go to the original blog now, that we got to the graph. The next step then was to, and I skipped this out from the notebook because there's quite a bit of itty-bitty code here, but the basic idea is to find the graph diameter of each of the graphs. That's the greatest distance from one side to the other, and do that for all of the word lengths. So I've got to find the words that produce the largest graph, and also there's the subgraphs. If you remember, they were disconnected. So it might be that the longest distance is from here to here, but it might be from here to here. I've got to go through every subgraph and check it for a diameter to pick out the graph that's got the greatest width. So that's what diameters does. Find the biggest, find the position of that, and I find that it's in the 6th word, and it's the 23rd subgraph of the 6th word. So picking that out of the myriad of graphs I have, this is now a completely connected, greatest diameter graph, and all I need to do now is to find the greatest distances, which is going to be something like this pixel, this vertex to this vertex. And so graph periphery finds the outer edges of that graph, so I've got my ends, and now I just simply have to find the shortest path across them, and that will give me our longest minimal word ladder path, which I thought was cool. I couldn't find it on the web. Nobody else seemed to have done it. So there it is, and then I called word data to generate a puzzle that you can get in that number of steps from charge to comedo, only passing through legal English words. Unfortunately, I had to retract it a bit later, which ruined the fact that the Guinness Book of Records wrote to me and asked if they could use this. And when I had to admit that I'd had to retract it and that there was a slightly better dictionary, that I think they got cold feet and thought it wasn't worth including because it never did make it in the end. Because I've forgotten that the other word dictionary we have includes plurals and verb conjugations, which I'd missed out, which seemed like a big omission. But yeah, I love these kinds of things. And in that vein we now get to the blog item that scored the best. It's when I took on Hangman. And this came about because of trying to stop myself being bored on a train. Where are we, blog? No, actually, let's get the original demonstration up. So while I was on a train to London, I wrote a Hangman game to pass the time. And I wrote the easy one first, where you do the guessing and the computer just says what you've got right and wrong. And the hardest part was just the user interface. And then I spent a really boring 3/4 of an hour on the underground thinking about how the other game would work and thinking about what the strategy is for a computer to play Hangman and trying to think, well, what do we do as a human? So I ended up coming up with the one where the human has to do the guessing, which is this one. And the way I concluded the strategy that we humans apply is a combination of elimination and frequency analysis. Actually, I won't bother playing this now. I'm sure you know how Hangman works. So what I concluded happens is you guess letters, first of all, on the most frequent. Everyone starts with the vowels, so we'll start with E. And then you get information back that tells you think words to exclude. So you can start eliminating the dictionary down. And you can do that both based on the letters that are or aren't in the word, but also their positions. So then you've got a dictionary of candidates, and what we end up doing is thinking, well, what's the most common letter out of what I've got left? Now, people tend to have said to me, oh, no, what you do is you look for patterns. If it ends in Y, then LY would be a good English word at the end. But actually, that's the same thing. If you go through all of the dictionary of words that end in Y, then the frequency of L goes right up, because L is very often the next to last letter. So it is still just frequency analysis. And so that's what I coded into this, and I was very pleased with it and left it on demonstrations. And it was about a year later, my daughter got old enough to play Hangman, and I said, oh, I wrote a program, and let's play with it. And it made her mad, because she couldn't win. It kept beating her, and she said to me, can you give me a harder word that it won't get? And we talked about it, and I realized, here's a cool idea. What's the hardest word in Hangman? And the way to do it is very simple. I'll just apply the algorithm to every word in the English language, and we'll count up how many guesses it takes. And there's some probabilistic stuff to deal with it not being boring and to deal with Nash equilibria type things. So I had to do it a few times. Now, fortunately, nobody asks me what I do, because this turned into a bit of an obsession, because the CPU time required is quite large. The computation is about 0.1 seconds, which is nothing playing the game. But a game could be 20 moves, so it could take a couple of seconds to evaluate a game. There's 100-odd thousand words in the English language. You've got to play them a lot of times to make sure that you're getting some convergence in the data. And so I had to write some Grid Mathematica code, and I didn't have a computer to run it on, so I was using Tom Wickham-Jones's computer, but it's a development machine, so I'm not supposed to use it during the day. So every night I ran the code, and every day I thought, this could be faster, and I retweaked it. So after about a week of, I probably spent about 2 full days at work on what's supposed to be a kind of side thing for when I've got spare time, I realized the code was completely wrong, and all the data was rubbish. So I had to do it all again. So I spent probably about 4 or 5 days on it. So it was something of a relief that when we shipped it, it broke the blog, because it got so many views from the social pickup. They put a new machine in, and that evening it got on the front page of Yahoo News, and it broke the blog machine again. And so these days, if you look back at the traffic for the Wolfram Alpha site, this is the Hangman blog item going live back in the middle of 2010, where it did about 500,000 views overnight and has now clocked up about 1 million, because it's sort of spread out. If you search on me now in images, you get spurious pictures of Hangman all over the place for what I look like. And perhaps the most surprising bit, hang on a second, why is that not? Oh, here we go. So I was somewhat surprised when about a year later I was genuinely watching this live on TV. I don't know if any of you know this, it's a fairly popular show in the UK is QI, but this came up.
What's the most difficult word to guess in Hangman?
Whatever you've got written there, I can tell you it's coal.
Anyway, they go on to make jokes.
About this, which you would appreciate as a games player. This person designed an algorithm to arrive at this conclusion, and he basically simulated 50 Hangman games for every word in the dictionary. That's 90,000 words, nearly 5 million games. He then took the 1,000 trickiest words, ran the game 3,000 times on each. In total, he played nearly 15 million games to reach the conclusion that actually the hardest is the word jazz. People just don't get the word.
And that was the final conclusion that I had. If actually, it's more fun if you look at the full data, because the jazz isn't that much fun. It's fun that it wins, but there are actually some, if you look at the longer words that have slightly less data, slightly less lower win rates, then there's actually much more fun words to be had at different lengths. So these are the best words, but I looked at the kind of best long words, and things like muzziness and bow-wowing I think are fantastic words to play, and wig-wagging. Much more fun than jazz, but yes, it turns out there's all kinds of cool things in the data, like if you don't know anything else, then on the whole, short words are better than long words. You'd think that long words would be more complicated, but you actually have more letters to get and more data once it starts coming. So 3- and 4-letter words are the way to go, and double letters are good because they make longer words look like short words. It seems to be the main conclusion. And it seems to follow a sort of general sort of power law as you go from the best words down to the worst words, what the win rate is. It turns out to be a bit more complicated because it depends on the style of game, on the shape of the hangman. I've taught on a gibbet that has 10 pieces, which is actually the easiest game. Lots of people play with 8-piece gibbets, which is obviously harder. You get fewer wrongs before you lose. So that's, while I've been a bit quiet recently, how I like to spend my time when I'm not actually doing proper work. And I have to say it was something of a relief that that blog item did pick up good traffic, because by the time I admitted how long I'd spent on it, I was being praised for success by that point. Anyway, I hope that's been interesting and insight into at least the way I look at Mathematica when I'm not doing real work. I'd happy to take any questions. I think I've used up my time, haven't I? Another 8 minutes? Oh, lots of time for questions. I could talk through another one then in that case.
All right, so I'm doing the running at the moment. Do you have any questions from anybody?
I'm always open to fun ideas, although I currently have in my blog folder about 20 ideas that are waiting for some attention, and a couple I'm stuck on. I'll put out a challenge to you, the one I'm stuck on. I tried to do some work on making a speed camera for cars based on sound. And the principle, it's another one of these things where I'm trying to reinvent the wheel. The principle's simple, that Doppler shift makes the car go as it passes you. And if I can just measure the difference, I know the speed. But there's so much noise to filter out, I can't get rid of it. So any ideas would be appreciated on that one.
Hi. Well, since we have a few minutes left, I was just reading this morning actually about the rock, paper, scissors problem. And apparently there is a Chinese professor who has put 360 students playing the game for a while. And he has found out that the best strategy is playing the same as the other guy played before. There is the full article on EPFL. And so just to give some insight on...
Yes, I saw that article actually. Yeah.
Exactly. So, and then the other stuff is that I just found out that I met a person I was following sometimes on the Wolfram Blog, which is you. I mean, I was aware of a few of these problems, but I'm not aware of the dynamics that they are, behind them. So you just mentioned you have about 20 ideas on a queue. And I don't know how it usually works. In a sense, do you sort of propose these ideas and you ask the community to contribute, or you just put, so to say, the solution and you ask the community to comment on them?
Yeah.
Or anything in between, or something else?
Usually what happens is I get a point where I'm just bored or don't feel like doing what I've been asked to do, and I pick out something out of my folder and think, that looks interesting, I'll play with that for a few minutes. And a few minutes turns into an afternoon or so, and I end up with a blog item. Occasionally they work the other way around, where I have had things where somebody from the blog team writes to me and says, hey, we could do with something about the new version, or we could do with something, well, Rita just asked me this week, hey, the World Cup, can you predict who's going to win? I'm not really the person, because I know nothing about football, but well, yes, that's always a safe prediction. So yeah, sometimes they come from the outside, and I have had a few kind of community suggestions where people write suggestions to me, and they sort of sit in the folder waiting for me to get to. So, usually it's just provoked by totally random thoughts. So I'm just working right now on...
Are you taking suggestions, John?
I am, yes. So here's one I'm working on right now that I've done I just have to add the narrative in, which I don't know why this popped into my head. When I saw the Knight's Tour for the first time on television when I was about 10 years old on the Paul Daniels magic show, where you get a knight to land on every square, and this guy solved it in his head live from a random start point. And I only learned later, of course, well, it's a tour, so he only has to know one solution, and wherever you start, you end up just going around that solution. So it was all showmanship. And then at college, I rethought it and tried to do it by pencil and paper and spent a whole afternoon moving knights around and never solved it. And I was thinking about that as driving into work just last week and realized, tour, that's just a standard graph theory function. So all we have to do is to find the, actually that isn't the solution I'm going to use. I'm going to use this, find Hamiltonian tour, and, I haven't initialized the code, but all we have to do is find the Hamiltonian tour of the right graph, and you can solve it. Okay, obviously need to clean this code up. So the only taxing part is to find the graph of the possible legal knight moves. And that's really easy as well, because the knight always moves root 5 squares. So you can just, again, enumerate all the permutations, and if they're root 5 distance apart, you end up with this graph. So I'll publish that one sometime next couple of weeks. But it's those kind of random thoughts that pop into your head that I just suddenly think, oh, I can do that. Yep.
Hello. You like to mix the different sounds, images, and so on. Could you perhaps make some computations with smells or things like that?
Sorry,
with flavors, with your smells?
Oh, right. Cool. Well, yes. Well, maybe when we've got device stuff, we'll be able to get that. And where would you get data for smells? That would be a good machine learning example, actually. Maybe if you could actually enumerate the values. There's a nice example, actually, I'm going to encourage him to write up, which I don't know if it got shown in the machine learning, which was trying to figure out from the food in something what nationality cuisine it came from. Did that get shown in the? Yeah, it did get shown. So that's quite a nice one for those sort of mixtures. But no, I'll have to think about that. Where would you get data for smells? There must be food scientists who have that data. Okay, I mean that's going to sit there in the back of my mind now.
We still have about 5 minutes left of John's talk, so if anybody does have any questions, feel free to ask.
Well,
no. Is that it? Okay.
Yeah, I won't bother talking through another one without having prepared.
Yeah.
So let's stop early.
Thank you very much.
It was meant to be a rest session, so 5 minutes of pure rest now. Thank you.